Hi, I'm Daniel and this is my video talk for EuroCG 2020. This project is joint work with Kevin and Sariel. The title of my talk is Sometimes Reliable Spanners of Almost Linear Size, and I promise that I will explain what we mean by the words sometimes and almost. So let's start with the basics. The graphs that we are working with are geometric. This means that their vertices are located in some d-dimensional Euclidean space, and their edges are straight line segments. They are weighted with the Euclidean distances. In such a graph, we say that a path between 2 points u and v is a t-path if it has a length at most t times the Euclidean distance of u and v. Further, we say that a geometric graph is a t-spanner if it has a t-path between all pairs of its points. This particular graph is a spanner with t equals 2 because it has a 2 path between all pairs of its points. A natural and interesting question about spanners is whether they can survive failures of their vertices. The notion of fault tolerance captures this. It has a parameter k, and the k-fault tolerance spanner has the property that it can withstand failures of at most k vertices. This means that if we delete some vertices from the graph, but no more than k, then the residual graph is still a t-spanner. We see immediately that k-fault tolerance spanner must have minimum degree at least k plus 1, otherwise there is a vertex that can be isolated by simply deleting its neighbors. Therefore, in order to have a linear sized fault tolerance spanner, we have to choose the parameter k to be a constant, which means that the spanner can only withstand constant sized failures. On the other extreme, if we set k to be proportional to n, where n is the number of vertices in the graph, then the spanner can withstand catastrophic failures. However, the size of the graph will be quadratic, which means that we essentially need the complete graph. So here's the following question. How can we construct geometric spanners that can survive catastrophic failures while having only a few, possibly linear number of edges? For this, the first candidate is the notion of reliable spanners. The setting is the same. We have a spanner G, and there is a failure or attack set which we denote by B. These are the vertices that we delete from the graph. The trick or difference compared to fault tolerance is that we allow some additional loss in the residual graph. We introduce a set B+, the so-called damage set, and we only require t-path between pairs of points that are outside of this damage set. However, it's important to note that the points that are only damaged but not failed are not deleted from the graph. These points can be still used to maintain t-paths between other vertices. So, a reliable spanner has the property that for any failure set there exists a damage set such that the size of the damage set is very small. It is bounded by 1 plus theta times the size of the failure set, where theta is some constant parameter between 0 and 1. And the residual graph has a t-path between all pairs of points that are outside of the damage set. Notice that there is no bound on the size of the failure set, thus reliable spanners can survive catastrophic failures. Let's see what do we know about them. Unfortunately, there is a lower bound of n log n edges, which means that we are still bounded away from having linear size, and we are not satisfied with this. So we are going to relax the notion of reliable spanners to allow randomization in the spanner constructions. That's how we arrive at the sometimes reliable spanners. We say that a random graph is reliable in expectation if the bound on the size of the damage set holds only in expectation. All other properties are unchanged. This is the notion that we are going to use. And I have good news, because using the notion of reliable spanners in expectation, we are able to construct spanners with linear or almost linear number of edges that can withstand catastrophic failures. We have two constructions, one for points on the line and one for higher dimensional point sets. The 1D construction is essentially a reliable skip list and has linear size. The higher dimensional construction uses a very powerful tool called locality sensitive orderings, along with our 1D construction, and there are some extra double and triple logarithmic factors in the size. This is what we meant by almost linear size in the title. Now let's see the 1D construction in more details. We have n points, say the integers from 1 to n. First, we give a structure of levels that can be thought as the levels of a skip list. For this, we use a binary tree where initially the leaves contain the points in increasing order from left to right. Then, we play an elimination tournament, which means that we flip a fair coin for each internal node of the tree to decide whether the left or right child wins, and the winner is promoted to the node. In this way, we end up with a logarithmic number of levels, and we are going to use these levels to define the edges of the graph. We add edges for each of the levels separately. On level I, for each point P, we connect it to the first Li neighbors to the left and the first Li neighbors to the right. Then the graph is obtained by taking the union of edges for all levels. Notice that Li is increasing with I, which means that points on higher levels have higher degrees and their edges are longer. This was the construction. It's very simple. It's also not hard to see that the size of the construction is linear. This is because the decay in the number of points per level is faster than the increase in the number of neighbors per level. Thus, we get a geometric sum and linear size. Now, we need to show that there are monotone paths between the majority of the points in the residual graph. In order to do this, we use a very intuitive idea, which is depicted on the figure. This is a path that we call a stairway, or, more precisely, a right stairway of point P. This is a monotone path starting from P, which goes to the right, and it's not only going to the right, but also climbs up in the level structure of the graph. This means that the next point is always present in some higher level than the previous one. Further, we say that the stairway is safe if none of its points are in the fail set, and the stairway is usable if it reaches far, essentially. So the last point of the stairway is among the last points of the graph. The idea is that if a point Q, which is on the right side of P, has a left stairway, then these stairways must cross each other at some level. Therefore, this gives us a monotone path between P and Q by doing some small adjustments at the point where the two stairways cross each other. This means that we can simply classify the points based on whether they do or do not have stairways. We say that a point is good if it has a safe and usable stairway in both directions. All other points are bad points. We know that there is a monotone path between any pair of good points in the residual graph. Therefore, we only need to bound the expected number of bad points in order to bound the expected loss. For this, it's enough to bound the probability of a point being bad, which of course depends heavily on the actual location of the failures. Intuitively, a point is more likely to be a bad point if it is close to the failure set, and it is more likely to be a good point if it is far from the failure set in some suitable sense. Thus, we do a classification based on how close a point is to the failure set, and after doing the math, we end up with the bound on the loss that we want. This was the one-dimensional construction. Now let me say a few words about our higher dimensional construction. Here, we have a set of n points in Rd, and we want to construct a 1 plus epsilon spanner that is reliable in expectation. The main tool that we use is a powerful result called locality sensitive orderings. This says that it's enough to maintain a few linear orderings to have the following property. For any fixed pair of points P and Q, there exists an order such that all points that are between P and Q according to this order are either very close to P or they are very close to Q. Okay, this is nice. But how can we make use of this result in our reliable spanner construction? Well, we simply compute this magic set of orderings and build our 1D construction for each of these orderings. And finally, we take the union of all edges. This is the construction. Why does it work? To see this, suppose that we want to find a 1 plus epsilon path between 2 points P and Q. We know that there is an order with the properties mentioned earlier, and the graph contains a corresponding subgraph. Since the 1D construction is reliable, there is a monotone path between P and Q according to the 1D order. This path corresponds to a 1 plus epsilon path in the original space, since it can have only one long edge that connects the locality of P and the locality of Q. All other edges are short-range edges in the small balls around P or Q. By choosing the parameters carefully, we can show that it's indeed a 1 plus epsilon path. This is the intuition behind the construction. To conclude, we can be happy now because we have spanner constructions that can survive catastrophic failures of their vertices while having only linear or almost linear size based on the dimension. Thank you for watching my video talk.